All right, folks. If you remember yesterday, I typed in. We're talking about the chi-square inverse, and the initial time that I just typed in chi-square. So I just want to reiterate the correct way of finding the command on Excel for this, and then what it refers to. I'm going to just write here. So obviously this is not what you would type. You would have to hit equal sign and actually put in values. But I'm going to give you like a descriptive way of remembering what you type in here for the chi-square inverse. Okay, so it should be, I just want to double check, chi-square dot inv. Okay, so it's going to be chi-square or chi sq dot inv. Okay, and then you're going to open that up. Okay, and you're going to type in. So right now, if I hit equals here, it's going to ask me for a probability. Okay, so the probability that they're asking for here is it's a left tail. It's always left tail, even though one of the chi-square values we're looking for is in the right tail. Okay, the way this is programmed is that it's always giving left tail areas. So the first thing you're going to do is you're going to type in alpha over 2, whatever that value ends up being. Is that okay with everybody? Okay. And then you're going to type in your degrees of freedom. Okay. That will give you the chi-squared left value. Okay. And I'll draw a picture that goes along with this here in a moment as well. The next thing you're going to do, so that's only giving you one value out of the chi-square. We need, since it's asymmetrical, we need both values. So you're going to go chi-square inverse again, okay? But now, instead of alpha over 2, it's going to be alpha. There's a couple different ways you can calculate this value. I think maybe the easiest one is you're going to do alpha over 2 plus whatever your confidence level was, and then type in your degrees of freedom after that. Okay? So a picture of this would be if we have our chi-squared okay, this area right here, okay, that is your alpha over 2 value. Okay, notice that from the left, that's a left tail probability, right? Okay, and we need to find, so we're trying, when we do this one right here, okay, that's the chi-squared, will be the left value, and it's providing that value, that chi-square value that attaches to this area or limits that area. Does that make sense? Okay. Now, the way that this function operates, or this command operates, to find this one over here. So I'm going to talk about that area as well, and that area is still, forgot to do attendance. All right. So, huh? All right. So this area over here is also alpha over 2. Okay. So if this was 5%, if this black shaded region was 5%, this is also 5%. But the way that the chi-squared command on Excel works is that it's going to require you to find this value right there on the chi-square. It's going to actually require you to type in this blue area there, all the area to the left of that value. Does that kind of make sense? Okay. And if we're thinking, obviously this here, this red area is the confidence level area that we're interested in. So if it's 90%, and this is 5%, so then cumulatively to the left, we'd be looking at 95% to get this chi-squared right value. Does that make sense? So those are the two things you're going to type in. Now, the one thing I need to hopefully we remember is that this chi-squared left value, when we put it into our formula, so our formula for our confidence interval is going to be it's going to be n minus 1 s squared over, now it's going to be your chi-square, it's actually the right value here, okay, and that'll be less than your variance, less than, and then we go n minus 1 s squared over chi-squared left. And people get that confused because if I'm thinking like left to right, this is the left ratio and this is the right ratio, correct? Okay, but the reason that's the case is because the chi-squared right, that value right there, is always going to be bigger than the chi-squared left, correct? If we look at the numerators here, are these numerators always the same right there? Okay, so let's just say they end up being 100. If they're both 100, okay, if I put a number, let's say they both put 5 there. Actually, let's put 4 there. If they're both 4, that means 20 is less than sigma squared is less than 20, right? So that means that would put them at the same value, okay? But what does this number have to be in comparison to this one so that this inequality is maintained? How does this number need to change so that this ratio becomes less than that? This needs to become bigger, right? So if I make this 5, I'm taking 100 divided by 5, that gives me 20, and this is now 25, so now I've got 20 less than sigma squared, less than 25, right? If I were to flip-flop these, if I were to put the left one here and the right one there, this number would be like a 4, and this one would be a 5, and I'd say 25 is less than sigma squared is less than 20, and that's false, right? Okay, so just be on the lookout for that. I never really pay attention to try to keep them straight. I just know that relationship about division. If I want to keep this inequality correct, then that denominator needs to be bigger than that denominator because the numerators are identical. Is that okay? Okay. So I think that's the best way for you guys to gain your chi-squared left and right values. Like I said yesterday, Desmos, I've been trying to search all the commands for Desmos. They don't have like a real nice page on Google that I've been able to find, or on Desmos' website that I've been able to find, that just lists all their commands. Can't find anything so far chi-square. TIA 384 has a chi-square like CDF, but doesn't have an inverse function. And GeoGebra does have something if you want to use GeoGebra, but you have to click on distribution. Sometimes, I don't know why mine does this, but I have to come down here and grab this and pull it all the way up. If I click on normal and then go to chi-squared, I'll type my degrees of freedom. So I'm just going to use the scenario we had yesterday. And I try to keep things, I always click on this one here to go left. So I'm going to find, it's just staying consistent with how we did with Excel, where it's cumulative to the left. So if I want alpha over 2, okay, if I go like 0.05, okay, I have to type in 0.05 right there, and that gives me then, that's the chi-squared value, chi-squared left that we were getting out of the table yesterday, okay. If I type in 0.95, there's the chi-square value that we were getting from the table yesterday, okay? That's as much as I've ever messed around with this. I don't know if I click on this one, if I can. Yeah, so here I can't. I'd like to be able to, you can move these around and see, you move these little arrows around and see, okay, how can I get this to be 90 with degrees of freedom of 24, but it's kind of a pain in the butt. If you knew, I think, what was it, 13.84, I think the other one's around 36, and that's pretty close to the 90% that we were looking for. But I think just using this left one and typing in there your alpha over 2 and then your alpha over 2 plus your confidence level, and it'll spit up back the chi-squared left, chi-squared right value that you need for your formula. Is that okay? All right. Yes. So that's exactly what this is. So to find so this is the confidence interval here for, so sigma is identified all the time as standard deviation, right? So if we square standard deviation, that gives us our variance. So that's the relationship between the two. So this formula is the confidence interval for variance. Okay? If I want the confidence interval for standard deviation, I just square root it all. Does that make sense? So when you go through on Math Excel and it asks you find the confidence interval of variance, and you find it, you use this thing right here, okay? And you got your two ending values, okay? Your the endpoints of your interval. Just take the square root of those endpoints, and then you have now the confidence interval for standard deviation. All right. There are, and I'm not going, we're not going to spend more than today on this. Okay. I'll go through these examples. You've got the homework assignment. We can ask. I can answer any questions you have on that the next couple of days. But in regards to notes or anything, that's going to be the last one. So I'm not going to spend a whole lot of time on this rounding rule. And there have been rounding rules throughout a lot of the things that we've done in the course, that there's just accepted techniques for rounding per really every situation that we go through. We haven't talked too much about them because my philosophy is, if you are using this statistics in an applicable way, maybe you're doing a research study, then you would know, to look up and say, well, okay, what is the rounding rule that I use using this test or using this confidence interval? Does that kind of make sense? I think there's just so many different rounding rules that we're going to get confused, so not even talk about it. Does that make sense? They're minor things. It's not a big deal. But it says rounding rule, rounding the same number of decimal places that are given in the sample variance or sample standard deviation. I put that in here. It might be a concern when you are typing things into Math Excel for this assignment, but again, if you are in the ballpark, 0.01, 0.05 incorrect in regards to your answers, let me know and I go back and put those points back on your assignment. Does that make sense? Get into an example here. It says find the 95% confidence interval for the variance and standard deviation of the nicotine content of cigarettes manufactured if a sample of 20 cigarettes has a standard deviation of 1.6 milligrams. Okay, we kind of talked about this yesterday in 7th period, and I think it makes sense to talk to you guys. Anything that has like medicine in it, okay, or like a drug like nicotine, okay. Not every, so if I go get like a bottle of Tylenol, and I look at every single tablet of Tylenol in there, and it says on the bottle that it's 80 milligrams for each tablet, I can probably be guaranteed that not a single one of those tablets actually has 80 milligrams of active ingredient in it. Does that make sense? Okay. It probably has 79.9998 milligrams, okay, or 80.0001 milligrams. Does that make sense? But on the dot, 80 milligrams is going to be very rare. Think about, you've done this in science class before, when you're weighing things, okay, or when you're measuring things in a graduated cylinder, or maybe even if you're measuring the length of something, you can only be as precise as the instrument that you're using to measure, right? So if my scale only goes to, let's say, tenths place for like measuring grams, okay, then when I have when it registers 8.1 grams, that's as precise as I can get. I know it's not 7 grams. I know it's not 9 grams. Okay, but it could be, when it says 8.1, the idea is it could be like 8.05 or it could be 8.14. Does that make sense? Like there's a range there that my scale is actually rounding down or up because it doesn't have the precision necessary to go to the hundreds place. Okay, so the more precise my instrument for measurement is, the more that I'm going to realize that when I look at those 80 milligrams, usually, okay, they're all going to be different. Okay, so the issue is, okay, well then if I'm going to take a tablet, okay, of medicine and not be confident that that tablet has the required amount of medicine in it to do its job, okay, so a pharmaceutical will say, okay, we can have this tolerance, we can have this error between maybe 0.001 milligrams either direction, above or below, right? Does that make sense? But if they had like a tolerance of like 10 milligrams, then that means that I could take each pill out of that bottle and say each one of those pills is somewhere between 70 milligrams and 90 milligrams, okay? Well, that would be a huge problem. Tylenol probably wouldn't be an issue, okay? But that'd be a huge problem if I'm taking like a medicine for like my thyroid or something like that, where a 10 milligram discrepancy could just throw everything out of whack. Does that make sense? Okay. Or if I'm taking a steroid, a certain dosage of a steroid could be a very, very bad thing if it's too low or too high. And then that variation back and forth, if it's a medicine that you're taking every day, I'm supposed to take 80 milligrams every day, and one day it's 70, one day it's 90, one day it's 80, one day it's 75, that's a problem, okay? My system can't get built up and used to it. Does that make sense? So that's kind of what's going on here, okay? Yes? Standard deviation. Okay. So here it says find the 95% confidence interval for the variance standard deviation of the nicotine content of cigarettes manufactured if a sample 20 cigarettes has a standard deviation of 1.6 milligrams. So what we're looking at here is, remember, n minus 1 s squared over chi squared. This is going to be the right value. I'm just going to put r for right. And that's going to be less than sigma squared, or my variance. And then it's going to be n minus 1 standard deviation squared over chi squared, my left value. The information provided here, so n is 20, correct? Okay, so n minus 1 would be 19. S is your standard deviation. Okay, now it's the S is standard deviation for the sample. Does that make sense? Sigma is the standard deviation for the population. Well, we're trying to estimate the standard deviation or the variance of the population. So then the best point estimate for that is standard deviation of the sample, right? Okay. So that's S squared. So that's going to be 1.6 in this case. 1.6, square that. Less than sigma squared. Less than, so it'd be 19 times 1.6 squared again. Now to find these denominators, okay, that's where we're going to turn to Excel and try to get rid of all the stuff I wrote or drew on here. All right, so I'm going to type these two things in. I'm going to hit equals chi square, the I and V, okay, alpha over 2. So we want 95% confidence. 95% confidence. So what is alpha? 0.05, okay? So alpha is the complement of your confidence level. Okay, so confidence level, 95% alpha, and this is going to be a terminology, a word that we're going to get used to. Alpha is going to start being eventually referred to as the level of significance. Okay, so in this case, 0.05. So alpha over 2 would be 0.005. 0.025. Does that make sense? Okay, so I'm trying to type in what I've got here in this first line, but using specific values. Okay, so alpha over 2, comma. Now my degrees of freedom we said was 19, correct? Okay, so my chi-squared left value is 8.91. Okay, I think that would be probably good enough rounding for us. I'm going to do the same thing then. I'm going to type in this bottom one. So chi-square, the INV, alpha over 2 plus my confidence level. Alpha over 2 was 0.025, right? Plus my confidence level now was 95. So what we'll type in here is 0.975. That would be the cumulative area to the left all the way up to my chi-squared right value. Again, degrees of freedom, going to be 19, and we get that value there. Okay, so I'm going to record those. So 8.906 and 32.85. So I know the larger one has to go here. The 32.85 needs to go there, and the 8.91 needs to go there. I always need the larger of the two chi-square values to be that first denominator. And now it's just a matter of plugging those in to whatever calculator you want to use. So we go 1.6 squared, so it's 19 times 1.6 squared, and that's all then divided by the 32.85 number, and then it was 19 times 1.6 squared, all divided by 8.91. So my confidence interval for variance, is 1.48 to 5.45. Okay. Now, if you remember, variance is if I'm comparing, it's talking about the spread of data. Right now, because it's squared, the variance interval here is in a different unit than what we were originally measuring. So when it said, we were talking about milligrams as a unit. So milligrams was the unit. So when I talk about variance, it's milligrams squared. So I can't really make a comparison there. So what we like to do then, okay, and this is what you would do on Math Excel. Math Excel, the first thing is going to ask you those two values right there. Does that make sense? Okay. But if I square root both of those, so I'm just going to take this as, I think I just go SQRT. Nope. Let's do it this way. Anybody remember what power I need to raise something to take the square root? 1/2. So I'm going to just raise this to the 0.5. And then I'll raise this to the 0.5. So I get that. Okay. So what this is telling me right now then is that the standard deviation is between 1.2 and 2.3 milligrams for this sample of 20 cigarettes. That makes sense? Okay. Which is telling me then, you know, obviously the smaller this interval is, okay, the better it is as a manufacturer. Okay. That means that the smaller this is, the more alike each one of the items that I am producing is. Does that make sense? Okay. If this was a huge band of values or interval of values, that would, let's say that we're talking about like P&G in the detergent scenario that we've been talking about in the last couple of days. If this was a huge interval, that would mean that I would have to go to Myers and weigh or at least hold each bottle that is on the shelf to make sure that I get the heaviest one as a consumer. Does that make sense? But if we can minimize this, make this as small as possible, then that tells me that each item is like the other items that I manufacture. Is that okay with everybody? And these are things then that companies want to look at to make sure that is what's happening with their machines. If it's not the case, then they have to stop production, go fix machines, and then reevaluate after they fix the machines to see if it actually, if their fix minimize these intervals. Is that okay? Maddie, do you have a question? This 32 number? Which that's going to be, so that 0.975 is what alpha over 2 was plus the given confidence level that they wanted in the original problem. Blades?
So there's a question where they give us all the numbers and we have to find the standard deviation.
Yes.
Beforehand.
Yes.
Do we use standard deviation of the population
sample? Because, and so I'm going to get an example of that. This one here, so example 2 says, find the 90% confidence interval for the variance and standard deviation of the price in dollars of an adult single-day ski lift ticket. The data represents a selected sample of nationwide ski resorts. Assume the variable is normally distributed. Okay. One thing to think about, guys, I know it's kind of a, is anybody really going to do this? Does anybody really care about the national ski ticket standard deviation interval? Probably not. Okay. But the scenario doesn't matter. Okay. Because all the scenarios you can interchange with one another. Okay. It's the procedure that we're going to do with the data that is important. So we've got these pieces of data. Okay. Remember, our formula requires us to have, I'll write this way, n minus 1, which is your degrees of freedom, times s squared over chi squared right, less than sigma squared, less than n minus 1, standard deviation squared of the sample, chi squared left. I need that value right there. I need the standard deviation of the sample. Throughout the scenario, they don't tell me. They don't give me the process data. We have to find it. Okay? Now, the thing is that this is not, this list of data is not the population, right? So when I go to Excel or Desmos or whatever it may be that I use to garner my standard deviation, I need to make sure that I use the correct command. So what I'm going to do here, I'm going to do it to the side real quick. I'm going to type in those raw data values. So we're going to go 59, 54, 53, 52, 51, 39, 49, 46, 49, 48. Okay? So we'll type those values in. And now here's the thing about using Excel, using software to do it. There's other, they're called statistical packages that people use, that researchers use to process their data. But before that, if we're thinking, even 40, 50 years ago, if we wanted to do this, the only way we can find S squared, okay, the standard deviation of the sample, or sorry, the variance of the sample, the only way we can do that is actually to run through the formula that we learned earlier in the year. Would you want to do that? No, okay. If you remember that formula, it was something like sigma squared is equal to the sum of x minus mu squared over n minus 1. And you would have to find mu, you'd have to find the average of these by hand. Then you would have to take each one of these and subtract each one of these away, or subtract the mean away from each one of these. You would then add all those up and divide them by n minus 1. You don't want to do that, right? That's very tedious. So without software packages, without Excel, this problem turns into, instead of like a 4 or 5 minute problem, it turns into maybe a 25-minute problem, okay? Because you got to do all those initial calculations first. But here I'm just going to go equals standard deviation okay, dot S because I have a sample here. I do not have the entire population. And I'm just going to highlight what that list is. Hit enter. So that is my standard deviation. And if you wanted to, I think there is, if I type in equals, you could type in var.s instead because the variance is s squared. Okay. This number here is that number squared. Does that make sense? Okay. So when you're typing this into your formula or using your formula, which says you're going n-1, so we had how many pieces of data here? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I counted 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 10. So n-1 would be 9. Okay. Now s squared. Okay, you can either type in 5.3 and square it, right? Or you got your degrees of freedom n-1 and just plug that number in directly. Is that okay with everybody? Less than sigma squared, less than 9 times 28.2. Okay, now I've got to find those chi-square values. Okay, I'm just going to come back up here to this old one. We wanted, so what they say, 90% confidence. So if I'm going 90% confidence, alpha over 2 would be 0.05, correct? Okay. Degrees of freedom is 9. Okay. The right chi-squared value, now this number right there needs to be alpha over 2 plus the confidence level. So alpha over 2 we said was 0.05. Confidence level is 90, so we're going 0.95. Degrees of freedom was 9. Hit enter. And those then become your denominators here. So we could put in right here the 16.92 number, and right here the 3.3, let's just say 3 number there. Is that okay with everybody? Okay. So I'll let you guys calculate those. But then once I have those, that is the interval for the variance, correct? What do I do with that interval then to find the interval for the standard deviation? Square root it. Okay. So regardless of the scenario, regardless of the story, if they give you the standard deviation of the sample like they did here, that's great. That's a bonus for us. Okay. But if they give us the raw data, if they give us a list, we're going to have to go to Excel or Desmos or whatever it may be, whatever program you're comfortable with, and you're going to have to figure out what the standard deviation is from that sample so that you can work inside the confidence interval. Okay. So that's something we can do? All right. So that assignment, open, still. My plan for tomorrow is to have a short little quiz over population proportions, P-hat, Q-hat, that stuff. Don't plan on it, but don't leave them at home.